are heated so extremely by the primary's X-ray flux that they expand violently and ablate away, fly off. Because total momentum is conserved, this massive high-velocity ejector impels the rest of the tamper pusher to recoil inwards with tremendous force, crushing the fusion fuel and the spark plug. The tamper pusher is built robustly enough to insulate the fusion fuel from the extreme heat outside, otherwise, the compression would be spoiled. Ablation mechanism firing sequence. Warhead before firing. The nested spheres at the top are the fission primary, the cylinders below are the fusion secondary device. Fission primary's explosives have detonated and collapsed the primary's fissile pit. The primary's fission reaction has run to completion, and the primary is now at several million degrees and radiating gamma and hard X-rays, heating up the inside of the hull room and the shield and secondary's tamper. The primary's reaction is over and it has expanded. The surface of the pusher for the secondary is now so hot that it is also ablating or expanding away, pushing the rest of the secondary, tamper fusion fuel, and fissile spark plug, inwards. The spark plug starts to fission. Not depicted, the radiation case is also ablating and expanding outwards, omitted for clarity of diagram. The secondary's fuel has started the fusion reaction and shortly will burn up. A fireball starts to form. Rough calculations for the basic ablation effect are relatively simple. The energy from the primary is distributed evenly onto all of the surfaces within the outer radiation case, with the components coming to a thermal equilibrium, and the effects of that thermal energy are then analyzed. The energy is mostly deposited within about 1 X-ray optical thickness of the tamper forward/pusher outer surface, and the temperature of that layer can then calculated. The velocity at which the surface then expands outwards is calculated and, from a basic Newtonian momentum balance, the velocity at which the rest of the tamper implodes inwards. Applying the more detailed form of those calculations to the IV mic device yields vaporized pusher gas expansion velocity of 290 km per second, 180 m forward/s, and an implosion velocity of perhaps 400 km forward/s, 250 m forward/s, if 3/4 of the total tamper forward/pusher mass is ablated off, the most energy efficient proportion. For the W80 the gas expansion velocity is roughly 410 km forward/s, 250 m forward/s, and the implosion velocity 570 km forward/s, 350 m forward/s. The pressure due to the ablating material is calculated to be 5.3 billion bars, 530 trillion pascals, in the IV mic device and 64 billion bars, 6.4 quadrillion pascals, in the W80 device. 19. Comparing implosion mechanisms. Comparing the three mechanisms proposed, it can be seen that mechanism pressure, TPA, IV mic W80 radiation pressure 7.3140 plasma pressure 35750 ablation pressure 530640. The calculated ablation pressure is 1 order of magnitude greater than the higher proposed plasma pressure and nearly 2 orders of magnitude greater than calculated radiation pressure. No mechanism to avoid the absorption of energy into the radiation case wall and the secondary tamper has been suggested, making ablation apparently unavoidable. The other mechanisms appear to be unneeded. United States Department of Defense official declassification reports indicate that foamed plastic materials are or may be used in radiation case liners, and despite the low direct plasma pressure they may be of use in delaying the ablation until energy has distributed evenly and a sufficient fraction has reached the secondary tamper forward/pusher. 20. Richard Rhodes' book Dark Sun stated that a 1-inch thick, 25 mm, layer of plastic foam was fixed to the lead liner of the inside of the Ivy mic steel casing using copper nails. Rhodes quotes several designers of that bomb explaining that the plastic foam layer inside the outer case is to delay ablation and thus recoil of the outer case. If the foam were not there, metal would ablate from the inside of the outer case with a large impulse, causing the casing to recoil outwards rapidly. The purpose of the casing is to contain the explosion for as long as possible, allowing as much X-ray ablation of the metallic surface of the secondary stage as possible, so it compresses the secondary efficiently, maximizing the fusion yield. Plastic foam has a low density, so causes a smaller impulse when it ablates than metal does. 20. Design variations. A number of possible variations to the weapon design have been proposed. Either the tamper or the casing have been proposed to be made of 235U, highly enriched uranium, in the final fission jacket. The far more expensive 235U is also fissionable with fast neutrons like the 238U in depleted or natural uranium, but its fission efficiency is higher. This because 235U nuclei also undergo fission by slow neutrons. 238U nuclei require a minimum energy of about 1 megaelectron-volt, 0.16 pJ, and because these slower neutrons are reproduced by other fissioning 235U nuclei in the jacket, in other words, 235U supports the nuclear chain reaction whereas 238U does not. Furthermore, a 235U jacket fosters neutron multiplication, whereas 238U nuclei consume fusion neutrons in the fast fission process. Using a final fissionable /fissile jacket of 235U would thus increase the yield of a tellurulum bomb above a depleted uranium or natural uranium jacket. This has been proposed specifically for W-87 warheads retrofitted to currently deployed LGM-30 Minuteman III ICBMs. In some descriptions, additional internal structures exist to protect the secondary from receiving excessive neutrons from the primary. The inside of the casing may or may not be specially machined to reflect the X-rays. X-ray reflection is not like light reflecting off of a mirror, but rather the reflector material is heated with X-rays, causing the material itself to emit X-rays, which then travel to the secondary. Two special variations exist that will be discussed in a subsequent section: the cryogenically cooled liquid deuterium device used for the Ivy mic test, and the putative design of the W-88 nuclear warhead, a small MIRV version of the tellurulum configuration with a prolet, or watermelon-shaped, primary and an elliptical secondary. Most bombs do not apparently have tertiary stages, that is, third compression stage, S, which are additional fusion stages compressed by a previous fusion stage. The fissioning of the last blanket of uranium, which provides about half the yield in large bombs, does not count as a stage in this terminology. The US tested three-stage bombs in several explosions, see Operation Red Wing, but is thought to have fielded only one such tertiary model, i.e., a bomb in which a fission stage, followed by a fusion stage, finally compresses yet another fusion stage. This US design was the heavy but highly efficient, i.e., nuclear weapon yield per unit bomb weight, 25 mount, 100 pj, B-41 nuclear bomb. 21. The Soviet Union is thought to have used multiple stages, including more than one tertiary fusion stage, in their 50 mount, 210 pj, 100 mount, 420 pj, in intended use. Tsar bomber, as with other bombs, however, the fissionable jacket could be replaced with lead in such a bomb, and in this one, for demonstration, it was. If any hydrogen bombs have been made from configurations other than those based on the tellurulum design, the fact of it is not publicly known. A possible exception to this is the Soviet early Sloika design. In essence, the tellurulum configuration relies on at least two instances of implosion occurring. First, The conventional, chemical, explosives in the primary would compress the fissile core, resulting in a fission explosion many times more powerful than that which chemical explosives could achieve alone. First stage. Second. The radiation from the fissioning of the primary would be used to compress and ignite the secondary fusion stage, resulting in a fusion explosion many times more powerful than the fission explosion alone. This chain of compression could conceivably be continued with an arbitrary number of tertiary fusion stages, each igniting more fusion fuel in the next stage. 22, 192, 193, 23. Although this is debated, see more, arbitrarily large yield debate. Finally, efficient bombs, but not so-called neutron bombs, end with the fissioning of the final natural uranium tamper, something that could not normally be achieved without the neutron flux provided with fusion reactions in secondary or tertiary stages. Such designs are suggested to be capable of being scaled up to an arbitrary large yield, with apparently as many fusion stages as desired. 22, 192, 193, 23. Potentially tough level of a doomsday device. However, usually such weapons were not more than a dozen megatons, which was generally considered enough to destroy even the most hardened practical targets. For example, a control facility such as the Cheyenne Mountain Complex. Even such large bombs have been replaced by smaller yield bunker buster type nuclear bombs. See more, nuclear bunker buster. As discussed above, for destruction of cities and non-hardened targets, breaking the mass of a single missile payload down into smaller MIRV bombs, in order to spread the energy of the explosions into a pancake area, is far more efficient in terms of area destruction per unit of bomb energy. This also applies to single bombs deliverable by cruise missile or other system, such as a bomber, resulting in most operational warheads in the US program having yields of less than 500 kt, 2100 tj. History. United States. The idea of a thermonuclear fusion bomb ignited by a smaller fission bomb was first proposed by Enrico Fermatto his colleague Edward Teller when they were talking at Columbia University in September 1941. 14. 207 at the start of what would become the Manhattan Project. 4. Teller spent much of the Manhattan Project attempting to figure out how to make the design work, preferring it over work on the atomic bomb, and over the last year of the project was assigned exclusively to the task. 14. 117. 248. However, once World War I ended, there was little impetus to devote many resources to the super, as it was then known. 24. 202. The first atomic bomb test by the Soviet Union in August 1949 came earlier than expected by Americans, and over the next several months there was an intense debate within the US government, military, and scientific communities regarding whether to proceed with development of the far more powerful super. 25. 1-2. The debate covered matters that were alternatively strategic, pragmatic, and moral. 25. 16. In their report of the General Advisory Committee, Robert Oppenheimer and colleagues concluded that the extreme danger to mankind inherent in the proposal to develop thermonuclear weapons wholly outweighs any military advantage. Despite the objections raised, on the 31st of January 1950, President Harry S. Truman made the decision to go forward with the development of the new weapon. 24. 212. 214. Operation Castle thermonuclear test. Castle Romeo shot Teller and other U.S. physicists struggled to find a workable design. 25. 91-92. Stanislaw Ulam, a co-worker of Teller, made the first key conceptual leaps towards a workable fusion design. Ulam's two innovations that rendered the fusion bomb practical were that compression of the thermonuclear fuel before extreme heating was a practical path towards the conditions needed for fusion, and the idea of staging or placing a separate thermonuclear component outside the fission primary component, and somehow using the primary to compress the secondary. Teller then realized that the gamma and X-ray radiation produced in the primary could transfer enough energy into the secondary to create a successful implosion and fusion burn, if the whole assembly was wrapped in a whole or radiation case. 4. Teller and his various proponents and detractors later disputed the degree